Aujourd'hui, on va avoir une présentation de cours Mathis de Arizona State University. Peut-être qu'il y en a parmi vous qui vous rappelez, on a eu une présentation il y a 2 ans pendant la pandémie de Sarah Walker qui nous a parlé de biosignatures. Cole, c'est un ancien étudiant de Sarah Walker. Et à Arizona State University encore. Et ensuite, Cole a fait un postdoc dans le laboratoire de Cronin qui vise à automatiser les expériences de reproduction de la vie en laboratoire. Ensuite, Cole a été un NASA Postdoctoral Fellow, a travaillé sur Assembly Theory notamment qui sont présentés, et à Santa Fe Institute également. Et il va ouvrir son lab en janvier prochain à Arizona State University, au Biodesign Institute. What is yours?
Thanks, Alex. I understood a small fraction of those words. So thanks for the introduction. I apologize for giving this talk in English. If only I knew another language. So I appreciate you all listening in English. So I sent an abstract for a talk with this title. And then I got here and I was talking to Alex and other people. And I realized many people here maybe are less interested about life detection in the solar system and are maybe more interested in life detection outside the solar system. So just to get an idea of like the disciplinary background of the people that I'm talking to, can you raise your hand if you're like an astronomer or astrophysicist? Okay, like everyone. Okay, cool. Okay, and then can you raise your hand if you are a planetary scientist or somebody that cares about anything inside the solar system? Okay, put your hand down if that thing is the sun. Okay, so I think I made the right choice. So I think I'm not going to give this talk. I'm going to give this talk, which is about a different set of papers. If you want to hear about assembly theory, I will like reference it a couple times here, but I'll talk about it much more in the colloquium that I'll give tomorrow. And if anyone was like just pins and needles really needed to know about the abstract that I sent, I'm very happy to chat here today, this afternoon, tomorrow, in the morning, and in the afternoon. So I think I will give this talk, which is based on a paper that I have out recently with a collaborator named Harrison Smith, who's at the Earth Life Science Institute in Tokyo. And okay, so just Alex said a lot of these things about me. In January, I'm starting my own lab at ASU. And right now I work in Sarah Walker's lab as a research coordinator and a NASA astrobiology fellow, PhD in physics. I have a background trying to connect experiments and theory. That's really where my sort of passion in science is. And I'm sort of torn between these different communities of like the astrobiology community and the complex system science community. I think of myself mostly as a theorist, even though I spend a lot of time trying to look at real data and talking to people that are doing experiments. But as a theorist, I think one of my jobs is to try to take a very, 10,000 foot, 10,000 meter maybe view of the field and point out where I think things are working and where things are not working. And so I'll just put my sort of cards on the table with this title. I think the answer to this question is no. And I expect that this is a controversial statement. And to make it clear what I'm saying, I think that we will not be able to detect life outside the solar system currently. The reason I think that we will not be able to do it is because we don't have a theory of life. And so I'll let that sort of sit a little bit. And then I'll also make one more thing clear. I expect people to interrupt me during the talk. Either because I've said something that doesn't make sense, I'm speaking too quickly or becoming incoherent, or because you disagree and you want to point out a point of disagreement. So I really, really strongly prefer that people, I prefer you err on the side of rude in attacking the intellectual ideas than err on the side of polite. So hopefully I can, by the end of this talk, I will at least have conveyed why I've come to this conclusion and why I think this maybe controversial statement is really important to interrogate. Okay, so here's an outline of what I'm going to do. I'm going to make the argument that astrobiology is stuck. I think this is actually not the most controversial part of my talk. I will go through a historical example of why this being stuck is really bad. And then I'll argue why this is even worse for exoplanet biosignatures. And then at the end, I'll say, okay, given this, what can we do to move forward? What should we be doing instead of what the field's doing just now? Okay. So this is maybe an interesting question, maybe a boring question, but it's sort of the central question in astrobiology and in the origin of life. And this is really the crux of why these fields are stuck. Sorry, I meant to start a timer, which I will do just now so I don't talk too much. So we don't know what life is. Many people have asked this question. Famously, the physicist Schrödinger asked this question in a series of lectures. And because we don't know what life is, we have a very hard time searching for life, right? And so if you go to an astrobiology conference and you ask this question to 100 different astrobiologists, you'll get 150 different answers. And it will depend on what their disciplinary background is, the types of experiments they do in the lab, and the last grant proposal they just submitted. And it's not for lack of trying. The core problem here is that most definitions of life that we come up with, if we say life is this, somebody comes along with a very robust counterexample. This is a sort of fundamental problem because it's not even clear if life and non-life are natural kinds. And what I mean by natural kind is like this philosophical concept dating back to Aristotle, which is like solids and liquids are clearly separable phenomena in the natural world that we can observe. And we can clearly define like a solid is different for these reasons from a liquid. And you cannot find a counterexample of a solid that is a liquid. Maybe there's some glass examples that a condensed matter physicist could come at me with, but in most of our experience, these are clearly separable concepts. It's not clear that the distinction life and non-life or abiotic worlds fit into the categories of natural kinds. So any sort of philosophical resolution of this question might need to challenge basic assumptions in science that date all the way back to Aristotle, right? And so I'm not going to try to do that here because I'm not a trained philosopher. Maybe Alex can help us out later, but that's above my pay grade. So instead, if you talk to people that are doing biosignature science, whether in the solar system or outside the solar system, you ask this question, like, what are we looking for when we look for life, right? And this, astrobiologists can get incredibly specific about. They can give you very detailed explanations for why they're looking for what they're looking for and how they're going to go about that, right? Most answers to this question from the exoplanet biosignature community are basically something like this, right? We're going to look for stars that have rocky planets orbiting them. We're going to try to focus on things that are about Earth size. And we're going to try to characterize the atmosphere of those planets. This is the goal, right? And with new instruments like JWST and instruments that are going to be coming in the next decades, we're going to get more and more information about the contents of the atmospheres of these planets. And we're going to learn other things about these planets. But really the things that we're focusing on that we think are going to be indicative of life are the compounds that are in the atmosphere. Okay, there's many more genres here. Does anyone want to disagree with that characterization of how we're going to look for life? All right, cool. So this is great, but this is not life detection. The reason this is not life detection is we can identify these compounds, but we cannot say how they got there. The surface processes are inaccessible to us in a way that's not just like, oh, the next generation telescope will be able to do this or that. It's just, we do not have a complete model of planetary evolution. We can't say this observation corresponds to this exact surface process or this ensemble of surface processes, right? The problem here is not just that we don't have a theory of life, it's that we don't have a complete theory of non-life. Okay, so let's look at an example about why this is such a huge problem. So I'm going to go deep into history now and talk about the Viking landers from the 1970s. Raise your hand if you've heard the story of the life detection experiments from the Viking landers. Okay, much smaller subset of the room. So this should be good for the people that haven't heard this. I think it's a really important lesson for anyone that thinks about life detection. So here's what the Viking landers looked like. Carl Sagan was standing next to them and helped design some of these experiments. 2 of them landed on Mars. If you know Martian geology, that's where they are, or Martian sort of geography, I guess. Okay, they had 4 related experiments that were connected to the life detection mission of the Viking lander, right? So this is 1976, more or less. They built an integrated system, which NASA sort of went away from for a while, to try to interrogate the question of whether or not there was life on Mars. These different payloads helped answer other questions, but this was like a big component of what they were trying to do. So I'm going to talk about each one of them and what they found in those experiments very briefly. So one experiment was what they called the gas exchange experiment. What they did was they basically took some soil from the Martian surface. It's not called soil because soil is generated in part by biology. It's called regolith, but I'm going to call it soil, and none of you are planetary scientists, so you'll forgive me. So they basically put soil in a human condition and just looked to see if gases were released from that soil. They saw when they did this, they added a little bit of water. There was like a rapid amount of O2 that was generated, and then slowly some CO2. This, they decided, was an abiotic signal. There was nothing really interesting there. They had gas chromatography mass spec. So they looked for organics, what they called complex organics in the soil. I'd argue that when your mass range is between 50 Daltons and 200 Daltons, you're not really seeing anything that's complex. But at the time, it was considered complex. They didn't see anything interesting there. It was almost spooky how few organics they saw. So abiotic, no signal of life there. They did a test to look for biomass building reactions. So basically, they looked to see if we take this soil and we put it in a sort of warm, comfortable environment, we put radio-labeled CO2 and carbon monoxide in the headspace, and we turn a light on and off, can we see a signature of something like photosynthesis? Can we see the soil sort of absorb the radio-labeled carbon out of the air and build something out of it, right? Because that seems to be something that life does. If you put some soil on Earth in a room and you shine a light on it, it'll draw some of the carbon out of the air and build biomass out of that. So they saw some small carbon uptake, but it didn't really respond to whether or not there was light. So there seemed to be no reason to think that this was driven biologically. Okay, then the last one was the so-called labeled release experiments. This was looking for biochemical reactions going the other way. So they scooped up some soil, they put it in this container, and they put really rich, sort of sugary, easy to digest carbon compounds in there, stuff that life on Earth would really like. That's a sort of growth media that you would use in a microbiology lab. And all of that media was radio labeled. So they knew the isotopic signature of the carbon in there is a bunch of carbon-13. And they looked to see what would happen when we added this, if that carbon would get sort of broken down and used as energy and released into the headspace as a gas. So you could count how much sort of radioactive material you saw in the headspace. And that would be a clear signal. They also designed an experiment where they would do the same thing, but before they added this sort of sugary sweet material, they would heat the system up to 145 degrees Celsius to sort of kill any life that was there. And then they would do the same thing to see if the response changed. This result was considered an ambiguous result. So I'll talk about that in detail because this is like the key result for understanding the Viking mission and the life detection objectives. Okay, so here's the data. So here's the experimental data. This is the control where they heated it up first. This is a measurement of time. Here is when they first added the data, or added the sort of sugary sweet material when they put it in. And then the vertical axis is measuring how much, basically a proxy for how much radioactive material you're seeing in the headspace. So how much carbon-13 is in the headspace. So nothing. You add this stuff, and instantly all of that carbon goes from the organic compounds into CO2 in the headspace. Okay, so that's super interesting. They added more of that stuff, and it didn't seem to make more of a difference. And then this is just the end of the experiment. They just purged it. Here's the control. So here, the only difference is before they added the radio-labeled carbon sources, they cooked the system first. They heated it up to kill everything there. They added the radio-labeled carbon, no increase. There's like a quick increase in the radioactive material in the headspace, but it's not anywhere near what it was in the experiment. So what these results mean is that they took Martian soil, they gave it some organic compounds. If they just give it the organic compounds, it rapidly converts those into CO2. If they cook it first, that response does not happen. So before the mission landed, before they even sent it up, this exact result had been pre-decided that this would be a positive life detection result. Okay, but we don't think there's life on Mars. So what's going on here? Like why, how do we explain this? And perhaps most importantly, why did we start this mission thinking this would be positive life detection and end thinking this is certainly not life detection? Anyone want to wager a guess?
Waiting for the answer. So why did we try this experiment before?
We did. Yeah, we did this on Earth. Yeah.
And did you try to use something that was completely sterile?
Yep. So let's see. Here's the control. So okay, so these are the same data that I just showed you, but these are so these are from the experiments. These dashed lines were an attempt to recreate the same result using completely sterile materials on Earth. So the explanation that they had for this was there must be something in the soil that's incredibly oxidizing, something like hydrogen peroxide, where as soon as carbon, sort of more reduced carbon hits it, it oxidizes it and pushes it all the way to CO2 right away. Hydrogen peroxide is a super simple compound that could do that. There's reason to think it might be stable given the temperatures and pressures on the Martian surface. So that was what this experiment was exploring, is the hypothesis that hydrogen peroxide could be in the soil and that this would have generated the response. Also, hydrogen peroxide, as you may know, you can go buy it at like the pharmacy. They keep it in like a black bottle because if it gets too hot or if it gets radiated from the sun, it decomposes into water, right? Okay, so what they see is if you had an analog for Martian soil and you put a bunch of hydrogen peroxide in it, you could recreate sort of the same result. You know, this was only one experiment, and maybe if you tweaked the Martian analog soil and the hydrogen peroxide in just the right way, you could get this result to be basically in between these two things that you saw. Right, but hydrogen peroxide, you've got to sell that in a black bottle because UV radiation will degrade it. Martian atmosphere is very thin. There's no magnetic field around Mars, so there's a lot of UV radiation at the surface. Here's the same thing where you, instead of just leaving the hydrogen peroxide by itself, you expose it to UV radiation at the same time. And so that sort of kills the result. So by the way, this G11, I think is maybe still alive today, but still believes that the Viking experiment detected life. He was one of the original authors. Still to this day is convinced that there's something there. Okay. So here's some interesting texts. So basically, between this result and the fact that the GCMS data didn't show any organics, that was enough to say, okay, maybe it's not hydrogen peroxide, but there's something oxidizing in the soil that would have created this result. And the fact that we didn't see any organics in the soil also supports the idea that it's not biological. Here's some analysis of that. Levin is basically arguing that, well, your GCMS data was not high enough resolution. Like, if the concentration of microbes was not high enough, we would have not seen anything on the GCMS anyways. So this combined with his sort of UV control on the hydrogen peroxide, he's arguing this is still ambiguous. We can't rule it out. Okay. Harold Klein was another, I think he might have been the PI on these missions. He was very high up in NASA at the time. Here's some text. Basically, this is just elaborating what I just said, that the decomposition of organic compounds by these oxidizing elements, whatever they were, would have explained this sort of positive result. And he's saying, you know, the labeled release experiments combined with the failure to detect organics, this is not life detection. Okay, so this is sort of where the current consensus is. This is all stuff I've said. So the real question was, okay, if it's not hydrogen peroxide, is there another oxidizing agent that it could be? Why didn't we expect this in the first place? Okay, and so here's the culprit for chlorate. On Earth, most of the chlorine that we have is in water. It's just this chlorine ion. But in very dry, very exposed environments, like, for example, the Atacama Desert here on Earth, a lot of the chlorine gets turned into perchlorate, just like this type of thing. It's really stable, so it doesn't react with other compounds or other oxidizers. At high temperatures, it can react. So this fact basically says that the heated, this fact that it reacts at high temperatures explains the control experiment, where what happened when you cooked the soil first is this stuff instantly reacted with all the other oxidizers around it, and then there was none left when you added the carbon source for it to continue oxidizing material. It's still not the most stable with respect to UV radiation, but we know from Earth at least it can be stable in the Atacama Desert, and it seems much more stable than hydrogen peroxide. Also, much later, the Phoenix lander detected perchlorates in the soil. So this is the current resolution of this ambiguity. But the Phoenix lander, that was like, that was early in my lifetime. So we had at least about 30 years of ambiguity sitting here about like, what is this data that we have from the Viking experiments? Is this actually light detection or not? And it took a very long time to resolve that. So yeah, this is more or less just what I said. The most confusing part about this is the existence of those perchlorates could also explain why there were no organics detected in the GCMS experiments. So whatever mechanism you have that's saying, well, when you heat this up, it oxidizes this material to get your ions in your GCMS, you have to heat them up. The nature of the experiment is you're sort of cooking things. So it could be that there are much more rich, diverse organics in Martian soil, but we didn't see them exactly for the reason that we saw this initial light detection result. So this sort of closes one door, but opens ambiguity somewhere else. Okay. So one more thing to say about this. So this is just sort of a summary of what happened here. This involved experiments on the surface, like controls. We could do this iterative process, come up with hypotheses, send future missions, refine our uncertainty. We do not have that option with exoplanet light detection. We're going to build bigger telescopes, of course. We'll probably do that no matter what we find with respect to biosignatures. So building bigger telescopes is a given, but those are still not going to allow us to do experiments. We're not going to be able to do controls. Right? This is maybe an annoying point to people that most spend their careers doing observations, but there's real power in experiments. Okay. So even with experimental controls, the results were ambiguous and continue to be confusing. Yes?
I just want to know what led the answers to this convincing for
Yeah, the publication sort of trail gets a little murky. He's, obviously pretty far along in his life. I don't know that he ever published anything in response to this. I think there is a paper where they try to interrogate it. I think so. He started publishing more with the other author, Patricia, and I can never say Patricia's last name, but it was Levin and something with an S. And I think they have one more paper that really focuses on this point of like, well, what should we see in the organics given these perchlorates? And I think that's an active area of research. And a lot of the Mars missions that have been planned in the last decade have had different ion sources that are not GC, exactly because of this reason. So the laser desorption ionization, which is on Mars 2020 and I think ExoMars, I'm getting that right, will be able to ionize, hopefully, material in a different way that doesn't necessarily activate that oxidation source. Yeah. Great question. Yeah. Okay. So resolving this ambiguity required coordination of lab experiments and additional information. And this is sort of the killer, I think. And this is where I'd be happy to prove wrong, but I think for exoplanets, all you ever get is the atmosphere, the little asterisk there, because like you can learn slightly more than that, but I think not, I think it's a difference in degree, maybe not a difference in kind, and it's all you ever get, right? And I think I'm going to bracket out the possibility of sending landers to outside the solar system in the next 300 years on purely political and economic grounds. If the coordination required to pull that off, I'm an American, it's not looking great for funding these things long term in the next few decades. Okay. This is the last point I'll make about the Viking landers. This was devastating for astrobiology funding in the United States. So this graph is how much money the United States was spending on astrobiology research. 88 was basically the resolution of the ambiguous Viking life detection results. And you see funding just drops to 0 for a decade. So, you know, as a soon-to-be faculty that wants to work on life detection, this terrifies me.
But I just don't why. Why? Because the results are ambiguous, and so it was checked. We have, you know,
No, it was ambiguous and a huge component of NASA specific. So there's a little bit of a NASA uniqueness here is the communication with the public. And they just had no idea how to manage what was being told to the public about whether or not there was life on Mars. And it was so, this is like a trauma that persists today in NASA. So for example, there's the Dragonfly mission to Titan. This is pitched as a prebiotic chemistry mission to Titan. But we don't know if there's life on Titan, right? So how can you do prebiotic chemistry if it's possibly a biological system, right? And that sort of strangeness, people have different opinions on this, but from what I can tell, comes from the fact that they don't want to call it a life detection mission. So the planetary science and sort of inside the solar system people have really internalized this sort of like almost trauma that happened and change the way that they talk about it. There's like this paper actually is really excellent analysis of what this did to the psychology of those missions. But this somehow, like there's a strangeness that I find in these communities where this is well known in the sort of solar system planetary science community and not discussed in the sort of exoplanet biosignature community. And I think here there's a huge risk that we're going to tell people things like JWST will detect life. And I think JWST will tell us many, many, many interesting things. But I don't think we're going to have less ambiguous results about life detection from JWST than we had from the Viking missions. Okay. So I hope I've convinced you that astrobiology is sort of stuck here. Does anyone want to make a counter argument or even?
I disagree.
You disagree? Okay.
Well, we can discuss that after, but the thing is that, of course, it looks like only ends atmosphere. But you don't necessarily need to have the whole theory of life to at least explore life as we know it here on Earth. Right? Sure. Okay, so of course we're stuck with this. That's the only thing, the easiest thing we can do is look for what we already know. But and I think what we're trying to do is to find something that is way out of equilibrium. You know, what you see, for example, oxygen, right? It's not because we'll detect oxygen, which is really far off.
Yeah.
That would be a biosignature. It's not it would be just water being used to scale.
Exactly.
So you can understand the context.
Exactly.
So, what is the planet? Is there any evidence for water-rich volatile? So, you know, and my gut feeling is that it's going to take many examples of things that looks really odd that you cannot explain with prebiotic. That will may say, oh, that may be there.
Sure. So okay. So
that way, we're not saying we're stuck. So there's still a path forward to make, you know, quite important step.
yes. So okay. So maybe stuck is the wrong word, but I think that the level of nuance that you just had in your response is not something I see sort of clearly discussed, right? So there's two things that I want to point out there. I think even if we found like an Earth 2.0, right, where we've got O2, which, okay, let's say we can clearly detect O2, methane, CO2, and water, all in coexistence. I think even then, it's not life detection, in that situation, what you've said is this ensemble of gases, which is very out of equilibrium, has been found. But because we don't know what the surface processes that generated that disequilibrium are, and our models for predicting that are still very poorly constrained, what we can say from that is we've detected these non-equilibrium gases, not we've detected life.
Sure, but that would still be a major step forward.
A major step forward, I agree.
Again, several example of those out of the case.
Right.
May make the case that we may have. I agree with you here, you know, I mean, really going to be extremely careful.
Right.
Not to say that there's something like fine. Strain habitability of especially indoor.
Right. Yeah.
But I think the point, I mean, it's going to be at best extremely ambiguous.
Yes, extremely ambiguous. And the last thing I want to point out is there are productive things that we could do, which I think I will hopefully get to. And one of them is anomaly detection, right? If your goal is let's go look at as many planets as possible, like our uncertainty about what planets can be and what their atmospheres can be is very, very high still. Let's just go collect as much data as we can and look for the cases that are the strangest, or maybe by analogy to Earth, sort of interesting for some reason. I think that's like the best thing to do, but I just think we have to be careful to call it anomaly detection or characterization of exoplanets and not life detection. Yeah.
They have planets like. Front page of newspaper.
Right. Yeah. Like if they see Earth 2.0, I think it's going to be hard, like for the newspapers to not say we've detected life, right? Which, by the way, and this is something I talk about in the paper that we had out in bioessays. That might be okay, you know, like I'm a scientist, I'm not a sociologist or a journalist. Half of Americans already think that aliens exist anyways, right? Like, and the New York Times has been publishing things about life detection like 3 times in the last 100 years. There's like multiple times in the 1910s where they were like, oh, our Martian neighbors built canals overnight. Seriously, front page of the New York Times, right? So maybe it's fine if we say, yeah, this might have been life detection and it's ambiguous and it turns out to be no. But there seems to be a lot of hand-wringing about false positives. And I don't know how we get around that given the constraints on our ability to observe other worlds outside the solar system. Okay, so maybe I need an asterisk here, not on that. Yeah. Okay, so I think the fundamental problem here is this. When we set out to do life detection on exoplanets, we're trying to make a claim about whether or not life is on a planet using features that are shared between life and non-life. So when I say this ensemble of gases, each of which could be produced by an abiotic mechanism, is life detection. Those gases are a feature, you know, I'm breathing out CO2 right now. That's a clear sign that I'm alive, right? But CO2 is not a biosignature because all sorts of things produce CO2 abiotically. So the real problem is we don't have anything that cleanly separates, well, I'll put another asterisk against anything. We don't have things that cleanly separate the realm of life from non-life. And in the case of biosignatures, of exoplanet biosignatures, we don't currently have candidates that clearly could ever create that bifurcation, right? Because the complex sort of organics that we look for, the signs of life that we would look for in the solar system, are not going to be accessible because the molecules are too big to be in the gas phase, or the time needed to observe like some kind of Darwinian process to unfold is not going to be like realistically observable. Okay, so yeah, and then this is, for the reasons I just said, particularly bad for exoplanet biosignatures. This is a problem for life detection inside the solar system and outside the solar system, right? The Viking missions had this same problem. They were looking for conversion of organics to CO2. CO2 is shared between non-living and living systems. That was a key source of the AMU. Okay. Here's one more thing I'll say because it's a Carl Sagan quote, and I like using Carl Sagan quotes. Right. So there's this great paper in Icarus, Carl Sagan, and this is very trendy now, I think, in the exoplanet community of like, would we detect life on Earth if we looked at it as an exoplanet? Carl Sagan was asking the same question and came to the conclusion that in the case for Mars, we would need kilometer scale resolution or lower to be able to detect life processes on the surface. That's a tall order for any satellite or any space telescope. Okay. And then, yeah. So usually at this point in the talk, people start asking me questions about their sort of preferred way to reduce our uncertainty about light detection. So temporal variation is often quoted as like, oh, maybe this can help us identify phenomena above and beyond what we would expect from abiotic systems. So on Earth, because we have seasons, if you look at the northern hemisphere, there's changes in the atmospheric composition based on when the winter hits and when the summer hits. This is a change in methane abundance on Mars, in the northern hemisphere of Mars. So if you think that time variation in your atmospheric abundances is enough to help you get out of biosignatures, you still have this abiotic control. So I don't think this is evidence of life on Mars. Maybe it is, but in either case, it's either evidence of life on Mars, or it's not, or this type of temporal seasonality is not a biosignature in and of itself. Okay. People will talk about surface biosignatures. There's like the red edge. This is a very famous thing. So for people that are not familiar, because of the nature of chlorophyll, it absorbs and emits light at a very specific wavelength. This dashed line is basically, if you were just looking at trees, like conifer trees, you would see this sharp edge where there's like a massive increase in the albedo right at a specific wavelength. This is like to do with the way chlorophyll or some kind of photosynthetic system must have this edge, because otherwise it's not able to gather solar energy and build biofats out of it. But these are not unambiguous either, because like a moon of Jupiter, Io, has like a similarly sharp edge, not quite as sharp, but it's there. Sulfur by itself has this very sharp edge. And cinnabar, this is like a weird mineral. So you would have to know, you'd have to have a hypothesis of how the photosynthetic system on that other world would work. And that would require a lot of knowledge about the history of their biochemistry, the details of their star. The star, maybe you could work it out, but I don't think you could predict the peak of, I don't think you could predict this red edge from conifers just from knowing the details of our sun. If you can, let's write a paper. That'd be cool. Okay, and then the last thing is people say like, well, what about a Bayesian approach? Well, this is gonna be like a long, extended, multi-decade process. We should sort of update our confidence in what we're detecting based on like our observations. And the real problem here is, again, that our priors are totally unconstrained.
This doesn't come from the Zoom.
Kind of feedback. Let's see if that just
The logging and unplugging is
always the trick. Okay. So people say, you know, what about a Bayesian approach? Can we just sort of update our confidence in the life hypothesis over time? And I would say that's not a bad idea, but what are you going to do about your priors? Right. So there's like a really excellent paper that explored this with the plume data from Enceladus inside the solar system. They concluded we could use the data in Enceladus's plume to claim that methanogenesis, a key biological biochemical pathway, is occurring in the subsurface of Enceladus's ocean. But the only way we can make that claim is if we have a strong prior about the likelihood of life occurring anyways. So basically, here is some very good observation that you have, and that your sort of credence in life given that observation. And here's how likely you think life is anyways. These are logarithmic scales, right? We have no idea where this prior should be. Okay, and so this is really, this is sort of conceptualizing, if we knew what the prior probability of life was on a given planet, then we could do a lot more. Then Bayesian approaches can save us in some way, right? But we don't, and we don't have a way to constrain it. So let's go.
Could you do something really silly? So like Earth is 4.5 billion years old. Life showed up, and we're not quite sure. But you could get a number. Some sort of.
You could, and somebody has. Actually, 3 people have. So Brandon Carter made an argument using that same logic in the 80s, I think 89. Rural Society, I think is where that's published. In 2012, some authors, Spiegel and Turner, I think, did the same thing. It's a little subtle because you have to ask 2 questions. One is, basically you have to, there's like an anthropic component, because you have to ask, what is the likelihood of life submergence? And also conditioned on the fact that you have a long enough evolutionary time to have organisms that can ponder their own emergence, because you only have this one sample and you're the sample. So there's like a weird loop there, but you could do that. And then more recently, Chen and Kipping did the same analysis, and then they asked a question: what other evidence would help constrain your prior? Would be another detection, experiments to constrain the timescale of emergence, so basically origin of life experiments, or better constraints on the geological and phylogenetic record. And they conclude that the best thing would be another detection, and short of that, origin of life experiments. Okay, so I think the fundamental problem here is we don't have good hypotheses for life detection missions. I think if all we're doing is, well, life made oxygen, so let's go look for oxygen. There's worse place to start, but it's not the best hypothesis, right? It's just a sort of hypothesis by analogy. The reason it's not great is because the rise of oxygen on Earth is a complicated process in and of itself. We don't know if it's generic to all life. We don't know if, even if you had the same biosphere unfold on a different planet, how deeply connected it is to our geochemistry. So there are like long-scale, multi-billion-year processes moving the oxidation state of the mantle and the atmosphere. And so half of the history of life on Earth, there's no oxygen in the atmosphere. So 50-50 chance that it's, even if you had an Earth-like planet with an Earth-like biosphere and you detected it, would you see oxygen in the atmosphere? So the reason I don't think it's a good hypothesis is because we can't connect it to experiments we can do easily in the lab, right? And so I think we have to ask this question instead of like, what are we hoping to learn about the universe when we look for life? I know this maybe seems like a subtle distinction, but the question is, what are we looking for that we think is impossible without life? What configurations of the world? Oxygen is one example of trying to do that, but it's not amenable to experiments here on Earth because the factors that control it are planetary scale processes that we can't easily interrogate in the lab. People are trying, and there's a lot of great work there. So just to make this clear, I want to maybe just make this analogy from the history of physics, where sort of in the post-Cold War era, there was like a lot of really interesting activity in particle accelerators around the world. And we were getting better and better models of particle physics, and quantum field theory sort of emerged out of this. At the same time, observational cosmology was getting very good, and we started getting insights into the large-scale structure of the universe in the very early days. We realized that in the very early universe, because of inflation, things were very hot and they were very close to each other. And those were the exact same conditions that were in our particle accelerators. And so there was a feedback loop that happens here where we realized that better theories of particle physics could constrain what we should look for in our sort of observational cosmology program. And the observations we made from our cosmology could give us better constraints for the correct theories of physics, right? So by realizing that there was an analogy between these two, they could sort of mutually constrain each other. And this was a huge leap forward because now you could couple a really difficult observational paradigm to a lab-based approach that we could interrogate here on Earth. So the argument I'll make is like right now we have this very difficult observational program in trying to characterize exoplanets and understand the diversity of possible worlds out there, abiotic or otherwise. And what we need to do is couple this to original life experiments here on Earth, where what we're trying to do is find situations that we think are impossible without life by pushing those as much as we can using prebiotic chemistry, right? Make the most interesting abiotic systems you can. What would those do on a planet? What are the observational signatures of those? So we need to sort of drive this coupling together. So this is sort of like there's skin in the game for the exoplanet biosignatures people in the origin of life community and vice versa. Because as I was saying earlier, if we find another detection, that's a huge boost to the origin of life community because now we have a better constraint on the prior probability of life. Okay. So forgive the analogy to physics. Most of you are physicists, so you won't be too mad at me about that. The biologists get up front about that. So this is the main point here. I think to get unstuck, what we need is hypotheses where we can interrogate the hypothesis not just with our observational program and our mission-based sort of exploration of the solar system, but also with lab experiments. Okay, and if you want to talk about, or if you want to hear about assembly theory, which I think satisfies this criteria, it has a hypothesis that we can pursue in the lab and makes observational predictions about what we should expect to see in biological worlds elsewhere, please come to my talk tomorrow or find me after this. Okay, in the meantime, I think there's 4 things we can do to learn about life that are not necessarily life detection on exoplanet systems. Here's what they are. And I'll talk about each one of these pretty quickly. I think they're more or less self-explanatory. So in the solar system, I think despite the sort of trauma of the Viking experiments, the things we can do in the solar system are tractable on a decade time scale, where we can send a mission, come up with a hypothesis, plan a new mission, and go follow it up to reduce our uncertainty. And the types of questions we can ask there, because we can do experiments on the surface, allow us to resolve ambiguity faster in a way that will actually help us sort of bootstrap our knowledge of planetary science and maybe biology. Okay, we can continue studying life on Earth with the goal of coming up with more and more universal features of life on Earth. Usually the challenge for astrobiology is like we only have one example of a biosphere, right? And we don't know what will be the same in different biospheres. All of us are descendants of Luca, the last unified common ancestor. And it's not clear if there's anything in common with all biological systems besides shared ancestry. If it's the case that there are universal principles, those are going to be the things that are most likely to generalize to other planets. So trying to understand what can we hope to generalize out of our own biosphere and coming up with hypotheses based on those is a way to try to like generate new sorts of observations or new targets for the exoplanet biosignature. So there's some people talking about like network biosignatures, for example, which is based on this idea. Okay, we can try to make de novo life in the lab. This is sort of the proposition that I put out earlier, where what you need to do is make the most interesting abiotic system you can with the fewest sort of constraints on the experiment that gives you the most lifelike or interesting thing that comes out the other side. Again, this will help us put constraints on what's possible abiotically. So if there's something we cannot make happen in the lab that we think would have a consequence on a planetary scale, that is really an ideal target for searching for life. Okay, and the last one is technosignatures. So technosignatures don't suffer from this problem in the same way, because any explanation for a technosignature is as absurd as any other, right? So to be clear, what I mean by technosignature here is not like small molecules in the atmosphere. So some people say like chlorofluorocarbons are a technosignature. I don't want to include those because we don't know what's possible in other worlds. What I mean is like directed contact. So if you guys have seen the movie Contact with Jodie Foster, I mean like getting the opening games of the Olympics beamed back at us, right? There are abiotic sources of radio waves. There are no abiotic sources of Olympic Games, right? And any abiotic explanation for the Olympic Games is as absurd as an intelligent civilization synthesis. So these are sort of in a different class. So maybe it's direct contact, maybe it's getting the digits of pi beamed at us in radio waves, or the Olympic Games, or searching for Dyson spheres or pulsars that are synchronized in some interesting way. You know, I think this is pretty speculative. This stuff is hard and maybe a little understudied, but this doesn't have quite the same problem as focusing on features that are shared between abiotic and biotic systems. Okay, so that's all I have to say. I think my timer, if it's correct, I've got like 10 minutes of discussion left at the end. This is just a recap. The reason I think astrobiology is stuck, and maybe I need a better word than stuck, is this ambiguity is going to be extremely prevalent. And so if we want to navigate that ambiguity, we need to think carefully about what our targets are and what we're actually trying to achieve. This is especially bad for exoplanets, but we do have ways forward to keep working on this in the meantime. Something I didn't put here is something like anomaly detection, where we just gather as much information as we can about as many planets as we can, and then do something, you know, just boilerplate like machine learning stuff of just like, which one of these are outliers? Let's go interrogate those and try to characterize them better. That might actually lead us to life detection. It's just that it's not currently justified based on our theory. So there's this weird, like, sort of philosophical, epistemological loop there where you might do something that is unjustified currently, which might later create the justification for doing it in the first place. This is a concept called hinge propositions. There's a really cool paper by a philosopher and an astrobiologist that I can share with people. Didn't have time for it in the slide about that. So anomaly detection, I think, is a productive thing to do going forward. I just don't think that's life detection. Okay, thanks for listening. Hopefully this was intellectually infuriating, but not offensive otherwise.
We're Canadians.
Yeah, exactly. And I'm really happy to have any questions or discuss more. Yeah, thank you.